Welcome and thanks for joining us. Today, we're going to be hearing from two guests. Andrea Norris is the director of the Center for Information Technology and Chief Information Officer for the National Institutes of Health. And after Andrea, we're going to hear from one of the NIH institutes when I speak with Alastair Thompson, the CIO of the National Heart, Lung, and Blood Institute. But Andrea, we're going to start with you as having the overall view here of NIH, a vast complex of agencies, some of which in the form of these institutes are pretty large and have large data sets in and of themselves. So maybe just to set the table for us, give us a sense of the scope of data and applications and activities that the NIH Central CIO office that you head overseas.
Yeah, thank you, Tom, and thank you for having me today. So NIH is a large federated environment. It's actually a collection of 27 separate institutes and centers. They are largely focused on a particular area of research and study in a particular area of disease or health area. But like my institute, the Center for Information Technology, is unique. It's one of 3 institutes that provide trans NIH kinds of support and services. So we run in the Center for Information Technology, we run all of the trans NIH technology. So we run a large supercomputer that is used by all of our researchers at more than 110 labs and facilities at NIH. We run a big distributed research network. We move 6 petabytes of data a day through that network and 300 terabytes of data every day to and from the internet. We run a bunch of the enterprise systems that are used, a variety of other kinds of services. And so it's a federation of institutes. And so we have big trans NIH technology, and then each institute runs their own specific kinds of systems. So NIH has about a $45 billion budget that about 85% of which we fund out to about 2,500 universities and medical centers around the country, in some cases the world, about 300,000 researchers each year to conduct basic translational and clinical research to advance discovery, to reduce disease, health issues, and improve the quality of life and health for everyone in the world. And so that's a big part of what NIH does. We also have intramural, what we call intramural researchers at these 100+ labs around our campus and near campus in Bethesda, Maryland, who are conducting bench lab research. Much of that has become very computationally intensive over the last 10 years. And then we have a broad administrative and management set of support capabilities that we have. We run the largest clinical research hospital in the world in Bethesda. This is often someone's last hope for help. We treat a lot of rare diseases and other issues where the health industry and commercial market just can't accommodate. So we're a big heterogeneous IT environment. We spend about $1.5 billion on technology each year. About $1 billion of that is in this distributed computational environment. And about 500 million of that is in the systems and applications that are used to support that science, that are distributed all around the campus. And so, so it's a fascinating world. A lot of what we support are in big data, scientific data repositories. That's a big chunk of where our technology and data resources are. A lot of our data is public access, public domain. We make it accessible to the public, general public, or especially, of course, to researchers around the world. We are a big supporter of public access data. And for science, we believe open access is the way to accelerate discovery. And so we have very large programmatic and discipline-specific data repositories with computational tools and job aids where researchers come to conduct their science.
like a big data theme kind of runs through all of these activities. And that leads to the question of the cloud, because the cloud is a logical place for many agencies to start hosting their data. In the case of NIH, a lot of that data is industry proprietary. It also has personal identifiable information, HIPAA data, HIPAA covered information in many cases. So besides just basic security, you've got some pretty deep requirements for stewardship of data. Tell us what you're doing with the cloud and how the cloud supports that, and also the health mission ultimately of NIH itself.
Yeah, so a number of years ago, about 5 to 6 years ago, NIH really realized that a lot of the future of some of our large data programs, we were watching the growth of our big data, big science data, and knew we needed to really get ahead of this. And so we invested heavily in what we call our data science programs across all of our institutes and at the NIH level, and established a new data science strategic plan that cut across all of our areas of study. And one key initiative that I've been happy to lead was something called the Strides Initiative, where we knew we needed to move these vast data repositories and data sets out of our on-premise and on-campus locations and into cloud environments, because they were too large to continue to compute on. They were too expensive. It wasn't even practical in some cases for researchers to go and be able to access and download to their local computers or systems. And so we wanted to be able to move the national research ecosystem to the cloud. And we knew that was a big challenge. This was 5, 6 years ago, right? And so we started thinking about how to do it. We didn't want to do it a researcher at a time. That was going to be too slow, too difficult. So we started talking with our industry, and we went and said, would you be willing to go with us down this experiential journey? We, NIH, fund as the largest funder of biomedical research in the world. We want to help inspire and encourage our researchers to move to the cloud. But we need to lower that cost bar. We need to do training. We need to do a variety of things. How can you help work with us to do that? And so we created the Strides program. It's a partnership. It's been with AWS and Google. And then last week we announced with Microsoft Azure. But to work with us in partnership to reduce that barrier, those cost barriers, to help work with us with training and professional services, to the universities where they have those researchers that we're funding. And so since that time, in just the last 2 years, we have moved more than 110 petabytes of scientific data into these cloud environments. Our researchers, our funded researchers, have used more than 100 million compute hours in the cloud. We've trained more than 4,000 researchers in how to use the cloud, everything from basics to advanced, and more importantly, how to do biomedical computing in the cloud, really how to do the kind of work we need to see our researchers do. And we're saving money because the discounts accrue to the collective research environment. And so the more we move, the more we the better the discounts are. And so we see it's a win-win for everyone. And we're seeing tremendous progress. So our big data programs, our cancer genomic and cancer data commons capabilities, you're going to hear from Alistair Thompson, who will share some of the amazing examples of things they're doing in the Heart, Lung, and Blood Institute. Our All of Us Precision Medicine initiative, where we're registering 1 million people to look for how we can do better, precise treatments for any number of diseases and activities. It's helped us with our COVID research and work in any number of ways. So in fact, when the genetic sequence of the COVID-19 virus was released in January, we leveraged our arrangements with under the STRIDES agreement in the cloud to make that available worldwide to researchers to start to do science almost immediately.
Wow.
So literally changing the way that we do science.
And let me ask you this, from a little bit drilling down into some of the technology with that 100 petabytes, which is an unbelievably hard to imagine number of scientific and medical data up in the cloud. You don't want to download it because then it would cost you petabytes of dollars. Do you then bring the compute to the data? And is there some architectural technique such that researchers, grantees, and your own scientists can get the answers they want, but they don't have to necessarily compute locally? How does that
That's generally the goal we're trying to support. It does depend on the repository or platform or program. Some programs, depending on the nature of the program or the data, will let researchers download data. But most of our bigger programs are creating workspaces and collaborative workspaces that really encourage the researcher to come to the cloud, come to the collaborative workspaces. There's a lot of already established analytic tools and utilities and capabilities for them to use, visualization tools, analytics, other resources. They can find or work with other researchers in these collaborative workspaces. They can do the work that they want to do. They can leave some of the work and data behind, which is what we're also encouraging. And so that's really the model we're moving to. We don't require that across the board, but that's the model we're encouraging to. Some of the data sets are just too large. You can't do it any other way. But that is the model we're moving towards.
And what is your strategy for managing knowledge of the data, the metadata, and simply making all of that data, once it's up there, that it remains discoverable, so therefore that it's useful? How do you catalog it all for the researchers?
So excellent. That's that. So we talk about making data fair, findable, accessible, interoperable, and reusable. My colleague, Dr. Susan Gregorek, who is our Chief Office of the Data Science at NIH, she often says, you know, we can probably do all the things. The interoperable is going to be one of the hardest. And I like to talk about the interoperable challenges at many levels. It's at the data level itself. You know, we have difference in common data elements, common data models, data standards, ontologies, different disciplines, different data domains. They have different ways of talking about data. These are long-standing challenges. Different ways of doing science, methods, techniques. Different, as I said, domains of science or domains of study. Technology challenges and working across different technologies or tools. The cloud platforms can make it challenging to work across platforms. But our goal is to be able to be seamlessly interoperable. The idea is that you're sitting anywhere in the world, you can easily find the data that you need, find the tools that you need in the context that you want to do your science in, and be able, it should be transparent to you where they're located. You should know the context in which they were collected. You should know the constraints by which you can use them. We will make sure we honor the constraints by which we are allowed to make them available. And that's a big part of what goes into constructing, you know, these data repositories and these assets. Because we honor not just the security and privacy, as you noted, but also the consent agreements by which people have contributed this data for science. And so that's the nirvana we're trying to reach. And so we're doing work at every one of those levels and across our teams, across our projects. Some of it's technology, some of it is practice methods and just data.
And you mentioned or hinted at this, the idea that you need the cloud interoperability among the commercial clouds. You name the big three that you are working with. And it strikes me that in a given research or grant situation, perhaps resources might be needed for a given grant fulfillment or a given piece of research within NIH that could take resources from more than one of those commercial clouds. How do you architect that? How do you manage that kind of interoperability such that it's transparent to that user that really needs to have it abstracted where that material he needs actually is?
So we are agnostic as to the platform. We leave that up to the researcher so we make the data accessible. And in fact, with our first two partners, we put our sequence read archive repository, which is the largest repository of genomic data in the world. We make that accessible in both Google and AWS. Those were our two partners at the time. We did not want to influence in any way any choices of the market. We leave it up to the researchers, and it's interesting across, we see choices in both. And so we work hard with the standards committees, the international standards committees, the other groups, our scientists. We're doing a lot with something we call RAS, Researcher Authentication Service, middleware that we're working on to make it easy for researchers to be able to log on and seamlessly move across these platforms if they have meet the requirements of NIH to be able to have access to certain data sets, and particularly controlled access data sets. And so we're doing a lot of work at multi-levels of this kind of challenge and working with the vendors. But, as we always have, we learn over and over again, standards can only take you but so far. And then it becomes real implementation. And so this is going to take us some time to get to that nirvana we're looking for.
Yeah, sort of cloud of clouds is the nirvana.
Right. And we expect that to be the reality. We do not expect to have a single cloud in the sky where all the data lives. We expect it to be a distributed world. In science, we're always looking for the next best thing. It's a world of experimentation. And so we want to make sure we're supporting that.
And many agencies, of course, at the ground level are talking about modernization. And many times that means updating their networks to modern protocols, specifically to take in cloud as a normal part of computing, but also redoing legacy applications, making different services available to constituents or to their own users. Modernization kind of means what you want it to mean. But would it be fair to say or describe how, in your words, how cloud is enabling NIH IT modernization, and maybe talk about some of the more mundane applications that just keep the agency running?
Yeah, NIH, we're so fortunate that NIH leadership really recognizes and values that that nexus of technology and science. And so has invested in technology proactively and preemptively. So for example, when COVID hit, we were able to pretty much continue our work without too much hiccup. Our researchers have continued to work in the labs from the beginning. The rest of our kind of staff that did not have to be either in the hospital or in the labs have been working remotely, but we had modernized our network sometime before that and had implemented really state-of-the-art collaborative technologies, because NIH is a collaborative organization with folks all around the world. And so we've conducted 3 million virtual meetings over the last year involving 10 million participants. We just did not really miss a beat. And we trained, initially, right in when we initially had to kind of all disperse, 10,000 folks right off the bat for those who weren't as familiar with some of the technologies and tools. In fact, we're very big about bringing students in, postdocs and postbacks, into our campus to work in the labs. Last summer was the first, right when it was at the height of the beginning of COVID. And so we were so disappointed. It was the first year, I think, ever we weren't able to really do that. This year, we were determined we were not going to let that happen. So we used technology and a lot of creativity to support our students again this summer, and had them all participate remotely. And so we're anxious to get the feedback on that. It's not ideal, but we were able to make it work. And I had the benefit of spending some time with them to get some of their thoughts about how to make that better. If hopefully we won't, but if we have to do that again. The technology, as I said, we're a large distributed computational environment, and we invest heavily in that. We have a few big systems: our financial system, our grants management system, our hospital systems. Those kind of systems are our big systems. The rest are largely smaller workflow administrative program support kinds of systems, or tied to our actual work in the labs themselves. But today, data is a research instrument, and computation is a lab tool. And so that's really, when we talk about technology and compute, that's really what it is at NIH. We're getting ready to do a new NIH IT strategic plan. We're going to kick off in September, and we're excited about that. Looking at things we've learned through the pandemic, and where over the next few years, the kinds of capabilities that we think are going to be really important for us to put in place, where we need to accelerate things that we might need to make some adjustments. There's certainly going to be some changes in what the future of the workplace is going to look like.
Sure.
We've got some folks thinking about that. And so we're anxious to get started with that.
And what's your best advice for other practitioners of IT at other agencies on just talking to cloud providers when you are going to have this deeper relationship and this enduring and mission critical relationship with them?
Oh, 2 things. I think it is all about the mission. It is all about the mission. So if you're not committed to the mission, if you're not in it for the mission, then then there's not much to talk about, because that's why we're here. And we're here to recognize that everyone's got their own interests they need to have accommodated, and we realize that that's a fair deal. But it is about the mission. Our goal is to accelerate discovery and improve health. And so our partners wanted to do that. That was important for us. And because if that wasn't important, then there was no way you're going to want to be in it for the long haul, right? And so that's the first thing. You really have to be committed to the mission, whatever that mission is. The second thing is you just it's a partnership. You know, it's irrespective of what the instrumentation is on how you make this work. You know, it does boil down to some of the people that you're going to work with and how you're going to think about doing this and you know, in a longer, you're expecting to be in this for a longer haul. And I think that's what causes you to think about it a little differently. NIH is an agency that does experimentation. I mean, that's what we do. And so we're very willing and interested in trying different things. And if it doesn't quite work, we'll move on to something else. That's what makes it wonderful, a wonderful place to be. And that's a little different than some organizations. And that makes it a little uncomfortable sometimes for companies that do business with us. You know, I think you have to kind of do that when you're trying to change culture, when you're trying to make big changes at national scale. I think those are the kinds of things you need to think about.
Andrea Norris is director of the Center for Information Technology, and she's the Chief Information Officer at the National Institutes of Health. Thank you so much. Mr. Thompson, good to have you with us.
Thank you. It's a pleasure to be here.
And we should begin maybe just with a brief overview of what particular activities and areas of medicine National Heart, Lung, and Blood Institute covers. I mean, you can imagine from the title.
Yeah, obviously we deal with heart, lung, and blood diseases and disorders, but we also deal with sleep. The National Sleep Center is part of NHLBI. Our focus is on understanding the basic science behind heart, lung, blood, and sleep disorders, and then using that to identify treatments and various other things to improve health for everyone. Heart disease, of course, being still the largest killer of Americans. It's a pretty big deal for us to try and address it.
All right, let's get to some of the cloud activities that you have going. Ms. Norris, the CIO of NIH writ large, promised you've got some really exciting things to talk about, some leading edge things with respect to cloud computing.
Yeah, we've been using cloud for our research programs for about 3 years now. One of the largest ones is our Transomics for Precision Medicine program, or TopMed. This is the world's largest set of genomic data. There's about 180,000 participants. One of the key things about TopMed is that it was specifically designed to reflect the diversity of the US population. And so it's one of the few data sets in the world that has a high population of people of African descent, of Asians and others. 180,000 genomes is about 3.8 petabytes of data. To work with that data, you have to use it in the cloud. Without the cloud, you'd be trying to download it, and you know, over whatever connection, your broadband connection you have, 3.8 petabytes is going to take a while, like years. And so we've established an environment called the NHLBI Biodata Catalyst, which is a cloud-based environment across Amazon and Google. And I'm sure Andrea's mentioned the STRIDES program. STRIDES has been a key part of making this successful because it's given us access to cloud's expertise from the cloud providers directly in their engineering support. But that data is now available to researchers, and they're looking for, in their needles in a haystack, of genome changes, variants we call them, that cause or have implications for heart, lung, blood, and sleep disorders. There've already been discoveries made in terms of impacts on cholesterol, on outcomes, and we're digging into it much, much deeper. It's been up there for about 2.5 years now, so we're sort of at the beginnings of it. But cloud is just so essential to us. The storage, the compute abilities, you can imagine computing across that kind of data takes extensive compute resources, and the elasticity of the cloud lets us spin up a large cluster of compute nodes, compute on it, do the analysis, and then shut them down again, rather than having a massive data center that's sitting there used, 20-30% of the time.
Got it. So just a question on the research itself, as an aside, by having this much more diverse database of people involved, while you can find out what the causes and effects are of a given disease, you can also see if there are racial or gender or some other disparities in people's susceptibility to different conditions too, I imagine.
Yeah, exactly. So particularly for people of African descent, humankind started in Africa. And so they have got a longer genetic history than those of us who were sort of latecomers. And so there's much more variation in the African population than there is for others. And that means that treatments that work perfectly well for other ethnicities may not work for people of African descent, or there may be specific things that make a particular medication work better for them, or make a particular medication damaging for them. And so being able to understand that across the population, across all ethnicities, is absolutely critical. One of the great challenges with genomic data across the world is that the vast majority of these data sets are white and male, frankly. And we've chosen to directly address that to help address health disparities.
And getting to the architecture of the cloud setup itself, you mentioned you don't have to download that petabyte or 3.8 petabytes of data. That means then, or just to put a finer point on it, the computing resources in terms of applications then go to the cloud as well. And just to put it simply, the answers come down, but not all the data.
That's right. So we work with teams from the Broad Institute in Boston and Seven Bridges Genomics, a commercial company. And they've built platforms across the top of this data that enable you to spin up these high-performance computing clusters. They use technologies like Docker to produce portable code of an analysis that you can run in multiple places. But it's that ability to take the compute to the data rather than trying to download it and then just download your results, your summary results that are much smaller, that make this kind of research feasible where it never was before.
And of course, there's a visualization behind you there. And does visualization, is that enabled by having this cloud compute cluster, the whole resource up there?
To some degree, when you're talking about genomic data, there's some very specific visualizations that make sense. And this is all what we call population science. So we're looking at large numbers of people that come from the NHLBI's cohort studies, like the Framingham Heart Study and the Jackson Heart Study, where we're looking at people over an extended period of time. And so we're looking at what are the changes in their genome over time and the way that it works. And so visualizing those changes, visualizing the variations between individuals, the correlation between a variance in the DNA and disease or reaction to a drug or whatever, we can visualize that very easily.
And give us a sense of how it works functionally for your grantees that are scientific and educational academic institutions, plus your own in-house researchers. How do they access these cloud resources? How do you make sure that what they're putting up there for their applications are safe, vetted, and so on? How does it all work mechanically?
So within the Biodata Catalyst, which is FSMA and FedRAMP moderate, it took a lot to get there, but we're there with most of them, still working on some last pieces of it. But this is very sensitive data from some sensitive populations in some cases. And so we work very hard to protect it. It's all FSMA moderate level, but we monitor it very closely. So the user logs into a web-based interface, and that gives them the ability to search for data using a variety of tools, including semantic knowledge tools that understand that, for instance, that myocardial infarction is actually heart attack, is actually several other things, to enable you to search through the phenotypic data, the clinical observations from these people, and identify a cohort that have the characteristics that you want. Maybe you're looking for people who have a BMI over 30 and have, systolic blood pressure above something else. But you're also looking for controls. You're looking for people to compare them against who don't have those things. And so it enables you to build this cohort and then go searching across all of that genomic data for variants that correlate with those particular things that you're looking for. And so it's a relatively simple task. This is something that just setting up an environment to do this would take months for a researcher. We call it getting to aim one, which is I'm ready to do my research. It would take months. You can just log in and you can start doing it because it's all there. and then generate your results and bring them down, which is just it's a game changer for the progress that we can make using this kind of data. Within Biodata Catalyst, we have a fellowship program where the Biodata Catalyst fellows are coming in, doing their research. They've been helping us actually build the platform out, but they're publishing now on things that would have taken them years in their local institutions, using their local institutions' compute facilities.
And how do you ensure the cybersecurity of all of this? Not that they would necessarily in the community of scientists and researchers in this field is highly collegial, but nevertheless, bad code can somehow get into anybody's system. And so it could corrupt the data in some manner, or go searching for PI, personally identifiable information in that data, and so on. How do you vet the applications before they are applied to that precious data?
So all of the people who are using this are registered with a bona fide research institution, and that institution holds them accountable to all the agreements for the use of NIH data. In order to get access to this data, you have to submit a data access request explaining what you're going to do with it and how you're going to use it. We have a data access committee that reviews it to make sure it's okay, and then approves it, and then reviews it every year. Are you using it the way that you said? To a degree, for us, even more important than the cybersecurity, which is held in a fairly conventional way, it's the matter of consent. So the participants in these studies consented for use of their data for certain purposes and not for others. Some of them are very broad, but some of them are quite specific. Our COPD gene study, which is looking at the genetic basis for COPD, they only want it used for lung diseases, perfectly reasonable. And so the platform is built with a layer of security to make sure that that consent is respected, that the data is used appropriately and securely, and that we have the institutions to reach back to hold people accountable. That means we monitor, we verify, we make sure that things are being done the way that they should. Our Docker containers come from a platform called DocStore, where there's verification of it, there's antivirus run on it. We're actually working with them at the moment on a certification program to only allow certain Docker containers to run on our most sensitive data, where they've actually had a human looking at the code and making sure that there's nothing untoward there.
And before we get into what your future projects in the cloud will be, I wanted to ask you, what are some of the lessons learned so far in these 3 or 4 years that you have had this 3.8 petabyte database up there and all the applications? What have you learned with respect to dealing with cloud service providers and what's possible with them for this very specialized field?
So I mentioned Strides before. Strides has been a tremendous asset to us. It gives us some sort of discounts in terms of the cloud providers, but getting direct engagement from the cloud engineers at Google and Amazon and Microsoft is just huge. We run a platform we call the TopMed imputation server, which is used to take the inexpensive genotype arrays of the kind that 23andMe and Ancestry.com use and extrapolate that using sophisticated statistics into a whole genome. This is built using that TopMed diverse platform so that you can actually impute the genomes of people of African descent much more reliably. There was a recent publication on that. And so the imputation server was built with the help of Amazon engineering. You know, it's a very complex task. It's done something like 18 million genomes since it started. So optimization is important. And so the team at the University of Michigan we worked with Amazon Cloud engineers directly to help tune it and make sure that it was going to work the most effectively we can.
It sounds like it's paved the way for other types of research projects. What do you have in mind for the next round?
So one of the big things we're working on now is a program called Aim Ahead. And this is driven by Congress appropriating some funds for NIH to fund research in AI and machine learning. One of the things that I'm sure we've all become highly aware of are the health disparities that we have in this country. The pandemic has shined a stark light on those disparities. Those disparities, sometimes now we're applying AI are coming from the AI itself. There's bias in those algorithms. If you go talk to Google, they will tell you that the easiest data to get hold of in terms of healthcare data for training machine learning comes from wealthy white populations. And so if you're trying to use that for African or Asian or whatever populations, then there's going to be a problem. So the Aim Ahead program is designed to address those health disparities, or work towards addressing those health disparities by understanding the disparities themselves and what their root causes are, social determinants of health and other things, but also to look at the biases in the algorithms and how we remove that bias. How do we first detect it and then remove it? And so this is a program where we're going to be working with historically Black colleges and universities, Hispanic serving organizations, tribal colleges, and others as the ones who have the greatest stake in addressing these things. And the goal of it is to apply cloud-based AI to these problems. These institutions are often not resourced as well as your Harvards and your MITs, as I'm sure you understand. And so cloud is makes a big difference for them. They can't build their own massive data center with GPUs, but working with companies like NVIDIA, we can provide access to their NVIDIA GPU cloud and allow them to make use of it, as well as putting specialized hardware in the universities and other institutions, workstations for people to be able to experiment and build out their models before running them at a huge scale on electronic health record data. This is at the very beginning at the moment. We're getting ready to make some awards for this, but we believe it's got a real chance of helping to address the health disparities, but really get into why these AI algorithms are showing some bias.
Interesting. You and I are not brand new to this whole field. And I guess when we got started, language involving commercial cloud computing, artificial intelligence algorithms, and regular use of petabyte-sized databases were not even in the language. They've only come in the past few years. So I imagine, as someone who is a CIO for a scientific organization, a medical research organization, you must see this as something not simply that makes what we've done easier, but enables the types of research and access to information that didn't even exist a few years ago.
Yeah, there are things which are they're not possible without the scale of the cloud, without the elasticity that it gives you. Another example we have within our intramural program, the researchers on the Bethesda campus, they've developed a mechanism for taking MRI data direct from a scanner, squirting it up to the cloud, computing on it to generate the actual image that you see, because what comes off the scanner may as well be encrypted noise from if you looked at it visually, and do that in near real time, to the point that they can do 3 or 4 frames a second of imagery construction. Compare that to your average MRI exam. If you've ever had one, you'll know you go into the machine, it does its thing, and then 40 minutes later you get to see the images. The use of this cloud enables us to do things like MRI guided cardiac catheterization with no radiation. Typically that's done under X-ray, and we're able to do it using MRI real time like this. This is now being used in various research institutions around the world, and it's only made available by the cloud. You couldn't do that in an ordinary hospital because you'd need a rack or 3 of GPUs sitting there to do it, but we can do it in the cloud. So there's entirely new fields of medicine and treatment that have become available because of the cloud.
And has cloud enabled, you mentioned intramural, and there are many institutes within NIH. You're one of the bigger ones, but I imagine there's a lot more ease of sharing information, even sharing of databases under the strictures you mentioned with respect to privacy and so on, among the institutes of NIH itself.
Indeed. And again, this is where Strides has really helped, because it's established an environment that's FSMA moderate certified, that any of these researchers can go into and work. It's one thing for a large institute like NHLBI to work with the cloud. We've got the technical expertise to be able to do that available. But smaller institutes who don't have the level of budget we do, Strides enables them to do things they couldn't do before in the cloud. We've paved the way. Strides has sort of laid the highway there for them, and now these smaller institutes are able to use it to generate more knowledge, and that leads to better health.
And what about the patients that are there that come in for clinical trials? Does their data also end up in the cloud for some sort of use? Because sometimes NIH is the provider of last resort for something nobody can cure or diseases nobody's ever seen before, and that must be enabled in some more efficacious way by having cloud facilities.
Yeah, so data sharing as a whole is really critical. You know, we talk about making data more fair, findable, accessible, interoperable, and reusable. And so both the intramural and the extramural, the institutions out around the country, are making heavy use of cloud for data sharing. Whether it's, you know, the simple kind where there's a standard data sharing tool used in academia called Figshare, where our investigators are posting basic science information. But at the same time, we have investigators in the clinical center who are making discoveries for these patients and posting that data, for instance, genomic data, to these large databases like TopMed and Biodata Catalyst. And because of that, they're able to see the difference between an individual with a rare disease and then this large population of people as well. And so cloud is becoming a way to do that in a much more effective way. And it's having a real impact on people and on patients.
And I imagine then in reverse, it allows the design of experiments and studies because of that facility being available that you could not have done before.
Yeah, and some of it is just having access to that scale of data. So one of the issues often in science is that you have what we call cases, which are people who have a particular disease, but you need to compare them against controls, people who don't have the disease, to see what are the differences. And so having that large scale of data available in the cloud that's diverse, you can find matching controls for cases that let you discover that, oh, there is a particular variant for this disease that is common across the 15 people we know in the world who have it, compared to the rest of the population. And it's not something which is just driven by ethnicity, for instance.
All right, just a final question, having lung in the name of your institute, and the COVID pandemic has had a lot to do with many people's lungs. Are you building a database here that could be used in future pandemics and future viral events that seem to center in the lungs for many, in this case, millions of people?
So there's a whole variety of things we've done around COVID, and not just the lungs. You know, one of the things that we learned fairly early in the pandemic is that SARS-CoV-2, the virus that causes COVID, attacks far more than just the lungs. Attacks the heart, the kidneys, the liver, the brain in some cases. And so it's become a very diverse disease. And this is part of the reason we believe that people suffer from what they call long COVID. And we've established a program called Recover, which is really designed at digging in to why people continue to suffer from these things. And at the center of that is data, whether it's electronic health record data that we're pulling out of the hospital systems that have been treating people, or leveraging our cohort studies to follow people who have long COVID, where we know what their history is. Bringing all of that data together in one place, it'll be at a place at Mass General Hospital in Boston, where all researchers can access it. We hope is going to really accelerate finding answers for these people who are really suffering right now.
Fascinating material. I want to thank our guest today. Alastair Thompson is the Chief Information Officer at the National Heart, Lung, and Blood Institute. Thanks so much.
It's been great being here.
Earlier, we heard from Andrea Norris, the Director of the Center for Information Technology and the CIO of the NIH. I'm Tom Temin. You're listening to Federal News Network. Let's go back to the studio now for what comes next in our Cloud Exchange.